Well, welcome friends to another lesson at educator.com in intermediate C++. Today we're going to look at input-output a little bit more detailed than we looked at in the introductory class. So in case you've been doing C++ or taking the introductory class or doing other programming languages, what C++ uses are streams of bytes for both input and output. This is from the Unix and C legacy. Input and output are just considered streams of bytes in almost any instance, any case you can think of, or we're just sending bytes out, we're getting bytes back, and how you put those bytes together is up to the application and the devices. So we'll review the class hierarchy in input-output, and we'll look at briefly at the buffer class hierarchy, but we don't really use the buffer class that much except to know that they're there. Now the iOS base is the base class for all input-output streams in C++, and it has class attributes. It's got some formatting methods, state information. Then we have the iOS subclass, which is derived from iOS base, and all the other input-output streams are derived from iOS. So it adds some numbers and some functions. It adds a few more things you can do with input-output. Now we've got our input classes, which is iStream, ifstream. Of course, iStream is an input stream. If is an input file stream. And then we have an input string stream. We can actually do input in and out to an actual string. So it's as if it was an external device, but it's not an external device. It's actually an internal string, which lets you do some of the formatting that it normally does for input and output to devices. You can do that formatting to a string. And of course, we got output classes. OStream, where there's an I, there's an O. Output file stream, OFstream, and OString stream. There's also an IOStream, which inherits from both input and output. And we have some status bits that allow us to detect errors. Or if the system detects an error, it will set one of the status bits and say, hey, something happened. You can use those status bits for parsing, but there is some cautions that we will talk about. We'll talk about using string stream for input-output to a string. And we'll talk about how and when to flush those buffers. Buffers are used in just about all input-output because it's more efficient that way. The application can just put a few bytes at a time, a few bytes at a time. The system will just buffer up those bytes until it has enough to have one blast of input-output, whichever it is. Let's say we're doing output. We say, well, we'll fill the buffer. When the buffer is full, the system will say, okay, here's my buffer, it's full. We'll send it all out to the data. And that'll generally be more efficient, especially like for disk drive, it's spinning around, whatever. So you say, I'm going to send us a couple of bytes there. We just got to wait for the disk to come around. Okay, here's your 3 bytes. So here's 5 more bytes. Well, we got to wait for the disk to come around again. So if you keep it into a buffer, when you wait for the disk to come around, well, you just put out the entire buffer all at once, and so it's more efficient with buffering. So all the input and output is automatically buffered. But there are occasions when you say, well, we need to flush out whatever. The buffer's not full yet. Send it out anyway. So we'll talk about how that's done. And we'll talk briefly about internationalization issues. If someone wants their program to do their output in some language other than American English, there's things that you need to do. Some more simple ones are like the European languages. Some of the more complex ones are some of the Asian languages, which actually take up more than 1 byte. You'll actually need to probably get a third-party library for some of those, but we'll talk briefly about some of those. So we have streams. C++ input-output uses byte streams. Any sort of data transfer is considered a stream of bytes. They just go out in order. So we'll send a stream of bytes to an output device, whether it's a printer, whether it's your terminal, whether it's a disk drive, a tape drive, whether it's your string. And receive a stream of bytes from the input device. So the user is typing things at the terminal. You're getting that stream of bytes, 1 byte at a time. Now, the bit shift operator is overloaded. And they picked that because it looked cool. It's, hey, we're outputting. This is our output to a stream output device. So they overloaded that too. It gives you a formatted output. It's called the insertion operator because it inserts bytes into the output stream. And it's typically used for formatted input. If you're doing unformatted input, you would use write function instead of this. And the other direction is input. So this is the write shift operator, which is overloaded for input. And it's called the extraction operator, which extracts data from the stream of data coming in. And again, that's used for formatted input. We've seen in the intro class some of the I/O manipulators for output. Well, some of those manipulators can also be used for input. So I'm going to format this data to be so many bytes long. I will expect to see, or so many digits long. I'm going to expect to get so many digits in my input. Or I want my input to be a hexadecimal number. So you would put your hex in your input stream so that the stream processor knows, oh, I'm supposed to parse this data as if it was a hexadecimal number or an octal number, etc. So quick look at the class hierarchy. IO base, of course, is the base class for all of the input-output streams. iOS has some type-dependent members. iStream inherits from iOS, and that gives you an input stream. And by default, there is already an instance called cin, which is declared as an iStream, which is your standard input. So if you're running a program that runs on the console, it will have a standard input and a standard output and a standard error. So CIN is your standard input. Now, if you have a GUI application, if you a graphical user interface, you'll probably use something else for your input, but we're not going to cover that in this class. Now, the other thing, besides an iStream, we have IFStream, which is a file stream. So we're going to read our stream from a file. We'll open the file, and we'll check the status to see if that file is opened successfully. If it is, we'll just start reading from the file. And of course, the iString stream. So we're going to declare a iString stream object and initialize it to a string, and then read input from it. That's one way of taking a arbitrary string and parsing it to see whether it's a number or if it's a float, etc. And of course, OStream, the opposite of input, is output. We have an output stream. And like we have CIN, we have COUT, your standard output, CERR, standard error, and CLOG, which you can redirect to a log file. But if you don't, it will default to CERR, just go to the same location for character output. And of course, you have your output file stream, your output string stream. And we have IOStream, which is multiply inherits from both the iStream and the OStream. And from it is derived FStream, so that's input and output to a file, and string stream is input and output to a string, or from a string. Now, each of these has its own buffer, and the buffer is there, it's available for you to look at. So we have classes for buffers. The buffering allows I/O to work more efficiently, as I mentioned. The system will take care of, the buffer's full, send stuff out. The buffer is full, it will provide it to the application. There are occasions when it needs to be flushed. So we have stream buff, buffers the data for iStream, OStream, and IOStream. File buff for IFStream, OFStream, and FStream. And of course, string buff for IO string stream. I hope you remembered that. So the attributes of the iOS base class allows you to do a number of things. It maintains various attributes that's used for all the subclasses. So we've got formatting flags. So we can set a bit in the iOS base. It's kind of the hard way of doing it, but you can do it. You can set a bit that says we will format the data left justified. Right, we will format the data to be right justified. Hex, we will format the data in hexadecimal format. So for example, if you have something like 16 hexadecimal, that would be 100, if I'm not mistaken. No, that's not right at all. My eraser doesn't work. Oh well. Never mind, I don't have time to really figure this out. I can't say an octal. If you have 8 in octal, that is 10, because it's 1 times 8 plus 0. So this 8 in decimal is 10 in octal. As a matter of fact, oh yeah, so here's what we have for hexadecimal. Octal is base 8. It's like a person who only has, imagine, if you will, there's a planet out there in the world where the intelligent life has only got 8 fingers instead of, maybe like this way, because you have to have an opposable thumb. So you've got a thumb and 3 fingers. So their decimal, their numerical system would be base 8. It would be called octal here. 16 is like, I can't demonstrate because I don't have that many fingers. But anyhow, so 16 in decimal, you convert it to hexadecimal, is 10. It's 1 times 16 plus 0. 256 would be 100 because it's 1 times 16 times 16, and then 0 and then 0. But that's neither here nor there, just a kind of a side issue here. So other bits that are kept in the iOS base class are the field width, how wide do you expect the input to be, how wide do you want the output to be, the precision, etc., etc. In the introductory class, we controlled those with I/O manipulators. What the I/O manipulators do is set these bits in the iOS base class. And some localization properties that change things like how decimal points are interpreted. In the United States, a decimal point means, at this point, from here we're going on to our fraction. So if we have 100.52, in the United States, we use a decimal point. Other countries use a comma. So they'll say 100, 52. And this is very important for input and output, not just, you want to display for a person from a European country, you want to display whichever decimal point they're expecting. It's also important on input, because on input, if you're expecting a decimal point, okay, we get a decimal point, we say 100.52, we'll put 100.52 into our floating point variable that's expecting it. If you're not using the decimal point as a decimal point, you're using the comma as a decimal point in other countries, then you would be inputting the comma. But if you're in the United States and you input the comma would be a field separator. So we get to the comma, okay, that's the end of our number. We're just going to put 100 into our number, and then the 52 will go into the next input. So it's very important to take care of, if you're dealing with an international customer, you need to worry about things like that. We won't talk too much about that, except to make you aware that you need to worry about it. Keep state information. We have the error state. Good basically means all the bits are 0. The bad bit has been set. The fail bit has been set. EOF stands for end of file. If you're reading from a file, you get to the end, the EOF bit will be set, which is, you can think of it as an error if you want. It's not really an error, but it's the type of thing to think about. And then we have an exception mask that says, if one of these bits gets set, throw an exception. The default is none of them are set, so it'll just set the bit, and you have to remember to go check. Or if you would prefer to throw an exception, you set the exception mask for which bits that you want the exception to be thrown for. So when the system sets one of those bits, such as fail, for example, then the exception will be thrown, and you'll go out of the normal flow of processing into your exception handler. Now we have the subclass iOS as additional members and methods to access the flags and attributes of the iOS base class. So we've got good as a member, which we'll go check. Is this good? Is this particular stream still good? We want to know if it's good before we continue. So we'll say, if cin good, then we'll process the rest of our stuff in. Or if we're reading something, if we've reached the end of file, we'll stop reading. We've reached the end of file. Fail typically happens like input. If you're parsing the input and there's something wrong, like if you ask for 11 and the user types 11, well, they can't parse that, so you'll get fail set. Bad tends to be worse than fail, such as like you're reading from a hard disk and the hard disk crashed, or you get something, you have a permission violation, some other nasty thing has happened. So you can use these functions to check the current state of the stream. You can also clear the current. You take all those bits. Okay, yeah, I know this particular operation failed. Let's clear all the bits and we'll try something else. We'll try again. And particularly for parsing, you can say, user, you gave me something I can't parse. I got to fail. So try again. So clear all the flags before asking them to try again. Otherwise, it'll still be set. Now, the operator not has been overloaded to fail. So instead of saying if cin good, or instead of saying if cin fail, you can say if not cin to test has this particular input stream failed. Or in the modern C++, you can use the keyword not. It's the same thing. We can read the current state, just bring in a byte that has, or a word that has the particular bit set. You can set the state. It doesn't unset them. If you want to unset them, you have to hit clear. That clears all of them. And the exceptions functions to set or clear which exception bits you want to throw an exception for if those particular bits are set. Now here's the error state flags, which are defined. The iOS gives you the namespace or the scope of the particular variable, and it will be EOF will go into the word flag and then the word bit. So you can, when you're setting exceptions, for example, you would say, like, say you want the fail bit to throw an exception. You say cin.exceptions, spell it right, get our scope operator, fail bit. So now, if some type of failure occurs, particularly if you have a parse error, an exception will be thrown. You might want to throw more than one exception, in which case you need to OR these bits together. So don't have a lot of room to demonstrate that. Let's demonstrate it anyway. Let's see if this erasure works now. No, it still doesn't work. Well, never mind. What we'll do, we'll put it right here. Instead of having this inside there, we'll have iOS fail bit, or, which is the operator that takes one bit pattern and performs an OR across all the bits with another bit pattern. So this is the fail bit pattern. And let's bring in bad bit. So we have that inside our parameter to the exceptions method, then you'll get an exception for either of these two bits. So we've got the end of file bit, the fail bit, the bad bit, and the good bit, which basically is the absence of the other bits. So if any of these bits are set, good will not be set. Our input classes. We've got the iStream input class. That's any sorts of input, particularly your standard input, which is what cin is. Or if you define any other types of input streams into your application, it will be either an iStream object or a derived from iStream object. So you get your default standard object instance. You can use the operator for formatted input from whatever that input stream is. You can use the get method to get one single character. Get line, which gives you a line of input. It is a character array when it's a member of the iStream class, which is one thing I really wish they had done this differently, but this is the way they've done it. We live with it. So you can say cin get line and then have a buffer. That has to be a character array buffer. So the buff would have to be defined as like char buff and then some size, let's say 200. And then you can use the get line member. Now there's also a global function with the same name, which works very similarly, but it uses string objects. So now you can say get line and say s and some delimiter such as the new line character. And then S would be a string object. And there's ignore. You say, well, I'm going to just flush out the buffer because I'm going to ignore everything until I get the letter H, for example. So you put in there that you want the letter H, and then, or like a new line, most common. So I want to ignore till I get to the end of the line. Or I'm finished processing, ignoring till I get to the end of the file. And of course, we have ifstream for file input, which adds additional memory functions. Open, of course. Is open, is this file open? Or is it did we close it? And close, among other file operations. But the open and close, of course, are going to be the ones you'll be using most of the time. And then iStringStream adds, not an open or a close, adds the str function to get or set the string buffer content. So we want to take some content, for example, like we don't know what it is. Let's put it into an iStringStream, and then we can run the operator, the less, right? That's our extraction operator. We will extract from the string stream whatever it is. We think it's an integer. Let's extract it into an integer. If it's not an integer, this operation, this operation from the iStringStream will set the fail bit. And if you have an exception set up for that, it'll throw an exception, or you just test for it afterwards. Of course, output classes. You've got OStream, which of course you've got cout, cerr, and clog, your standard output object instances. You've got your insertion operator overloaded from the bit shift for formatted output, and that's where you have the various things like if it's an integer, you want it to be printed out as an integer. So you want a character for for example, if your number happens to be equal to 27, but your formatted output is going to send a character 2 to the output stream, followed by the character 7 sent to the output stream. And you do have a flush method, which says, okay, I know you've been keeping this stuff in a buffer, but I need this data to go out now for whatever reason, so let's flush it. Put puts out a single character. Write, of course, puts out a character array buffer. So you keep all your data into a character array, and you have that formatted the way you need it formatted, or raw data, as it may happen to be, and you want to write all of those characters out to your output device. Your OF stream, of course, now we have the file derivation of the output stream, which, of course, has open, is it open, and close, your file operations. And, of course, the string stream device, or object derivation, for string character streams. And it also has the str for getting your string data in and out of your output stream object. Now we do have some multiple inheritance going on. The IO stream multiply inherits from both the input and the output streams. So everything you can do with an input stream can be done with an IO stream. Everything that can be done with an output stream can be done with an IO stream. Not necessarily at the same time, but you can do that. So this is a classic example of multiple inheritance. It also includes the classic problems that can happen with multiple inheritance, which we're not going to talk about. Now, to get the IO stream, the input, the I stream, the O stream, the IO stream, you include the IO stream header file. That gives you I stream, O stream, IO stream definitions. F stream inherits from IO stream. So that gives you input and output from a file, or to a file. And you include the F stream header, which gives you the input file stream, the output file stream, and the file stream objects. And string stream inherits from IO stream also. Again, now we're talking about I string stream, O string stream. Now they didn't spell this out for their header file, so it's just S stream, which gives you I string stream, O string stream, and string stream definitions in that particular include file. Now, here's how there's all sorts of different things that can go wrong, input and output. So never assume your I/O is going to work perfectly. You need to check your status bits. So here's one way of checking the status bits, is just do a test. So we're going to include the fstream include file. We're going to define an input file called myfile, and we're going to open that file. It happens to be called myfile.txt. Now, if it's good, so we're checking that status bit. If it's good, it's good. We can do whatever we need to do to it. So we can take the myfile ifstream object, like cin, only now it's going from file, and put it into my data. And my data should have been declared up here as being whatever. Let's say it's a float, for want of anything better, and call it my data. So we will be expecting floating point numbers to be in that particular file. Now, if it's not a floating point number, if the first word in this file, my file text, is my file, for example, well, that's not a floating point number. So you'll get a failure. It will fail to parse that into a floating point number. So this will be true, and you'll have a problem. You need to handle it. Now, the other way we can take care of this are with using exceptions. So we have our myfile input file stream, and we're calling the exceptions method. We want to throw an exception if it fails, or if we get a bad bit. If something bad happens or it fails, throw an exception. So we'll do the same thing we did before. Open the file. So what will happen if that file is not there, if we don't have permission to read that file, if the disk crashed, whatever the case is, we'll get an exception. So we'll have to handle whatever that exception is. If we don't get an exception, everything's fine, we'll just continue processing. So now we can say my file, load that into my data. The same thing, if we have the text my file here, when we're supposed to be having a floating point number, an exception will be thrown for the fail bit, and we have to handle that in our exception handler. Now, a bit of caution is using the fail bit to parse your input. It's set on the format input if the input cannot be parsed, but not every incorrect input will fail parsing. And here's a classic example. Okay, we have the CIN, we'll set the exceptions, we'll set the fail bit. We want to find out if we have a parse error on something. So we'll print out something like, we'll have a cout that says enter your data, however you want to work that out. And then we have a try block that gets the data, gets my data, followed by another one that says get your data. And we'll catch the exception that'll get thrown for, then we'll say input parse fail. So if the user enters 11, you'll get an exception. But if the user enters 10,300 and puts a comma in there, which is very common, it won't throw an exception. What it'll do is it'll take my data and set that to 10, and take your data and set that to 300, which is probably not what you want to do, which is why I always recommend just, if you have an input, read an entire line, parse the entire line as if it was one singular piece of data. And then when you're ready for the next one, then you prompt the user, give me your next piece of data. Read the entire line. Load it into a string, for example. And so if you have something where they put a comma in or some other weird character, you can detect that, and then you can hit it back to the user, hey, don't do that. So 11 will get caught, 10,300 will not get caught. So here's why we're talking about the string stream. The string stream object can be used for input and output. You can do your formatted input and formatted output into a actual string. Once you have that string, you can do whatever you want with it. So if you're outputting, you can do all your formatted output into a string stream, and then take that stream and then put that to the final device. You might want to look at it first. You might test it to see if our formatting caused some problem that we're not expecting. So we'll test it before outputting it. Or you can input into a string stream and then do your CIN, your format input from the string stream, and then check to see if there's more data after the CIN is finished. And well, wait a minute, there's more data after. The user wants to put a comma in there or did something else strange. So it gives you an additional buffer that's under the programmer's complete control. You can inspect it, you can do things with it, do whatever you want. It's often used for number conversions. C++ doesn't have a lot of functions available like many other languages have. So I want to take this string, I want to parse it into a number. Or I want to take this number and format it into a string. Those functions don't exist. But you can use the string stream to do that sort of thing. For example, we'll have a string, a buffer, that we're going to do. Okay, first we're bringing in the library. We're going to declare a one-line input buffer. And we're going to get that line from the user or from the input, the standard input, wherever it's coming from. There's the buff, and we're going to go all the way until we get to the new line. So that's one line of data that has been stored in the string. Now we're going to move that into our input string stream, and we just call it ISS. So we're copying the buffer into there, and we have an integer value, and we want that input to be a hexadecimal number. So we're going to input, and this will set the iOS base flags to say the input from henceforth shall be hexadecimal, and then load that into a value. So it will parse the hexadecimal value. Now, if the user puts in there 16, that will cause a failure. So we will test for that and say, hey, we cannot parse that. If the user puts in A, that will get parsed as a hexadecimal number, and the result will be value will be equal to 10. So that's, and then we print it out. So we have this little program. You can run this. You put in the hexadecimal number, and it will print out what the decimal value is. So here we have a quick little hexadecimal to decimal converter using the input and output to a string stream. Now, when do we flush our data? Sometimes buffering is very good for efficiency. There are occasions when you don't want efficiency. Sometimes you need to synchronize with some other independent process. Sometimes you need to synchronize with user interaction. I've seen more bugs where people have written some code and they don't understand, why is this working this way? Why is it printing this up here and that down there? Well, it's because the buffer wasn't full yet, so it just held on to the data. You particularly have this issue when people have cout mixed with cair. They use different buffers. So why is it giving me the error message here and then the data down here, or the data up here and the error message down here? Well, the buffer's filled up at different times. So you say, well, I don't want to use a buffer for my error message, for example, or for my logging messages. A lot of things, you have a buffer for your logging. I need to know that something happened. Well, if your system crashes before your log buffer is full, your log buffer could be full of important information that tells you why that thing is crashing. So you fill out the log, you flush it out. So the data goes out to your log file, and then proceeds, and then it crashes. Well, you know that the log is the last thing that was logged. You know that log is good. You can look at that and say, oh, well, this value is not what it's supposed to be. That's why the system crashed. So here's how we flush the input. There's no input flush. There should be, but there isn't. So we have an integer number. We want to put it into the number. Now, if it fails, we will print out there, we can't parse a number, and our default is going to be to set it to -1. And then we want to clear our error bits because we want to ask the user, hey, try again. And the user might have done something like 10,100, or might have done something 10, comma 15, whatever. So we would have read to the 10, attempted to parse it, failed, but the plus and 15 is still in the buffer, and it'll be ready for the next time your process goes to a cin. So we want to say, no, ignore. Int max is the maximum possible integers. You want to ignore everything until we get to the new line that the user would have had to have entered in order for it to come into your application. Your output flush, like I said, you have your log. Error XX occurred. If you want the user to know, or you want your system administrator to know, or something, you want somebody to know that we got this error before proceeding. So we flush that out, so we'll know at this stage of our application processing that this message will have been put into the log file. And then we'll proceed. If we crash now, we don't have to worry about this information is there. Someone can read that information and do something about it. If you don't flush that, you could crash, and important information is sitting there in the buffer, and it's lost. So there's our flushing for input and for output. Briefly, there are internationalization problems that you need to be cognizant of, especially if you're writing code that's going to be run by somebody in other languages and other cultures. And for example, in the United States, our date format, we typically have month with a slash, day with a slash, and then the year. Our decimal point numbers are 999, then we have a decimal point, and then 99. Our thousand separator is the comma. Other countries do different things. They'll have the day, and then the month, and then the year, and separated by a period. The comma will be used for the decimal point, and then a period is used for the thousand separator. So these are things that you need to worry about. Now, one of the things you can do, if you have the locale installed on the machine, you can imbue the output with whatever the locale is. Now, I've tried this on my PC, and it doesn't work on my PC, probably because my PC does not have the various different locales installed. I tried this on my Linux machine, and it worked perfectly. What I did, I put in here as locale, I put German. And when I printed out my numbers, I got the German version of how decimal points are used. And there are all sorts of different ways. I've seen documentation, again, still German. You have lowercase de, which stands for Deutsch, underscore capital DE. So that's another way of saying this is the German locale. But again, the locale has to be installed on the machine, otherwise it won't work. Now, Asian languages have the additional issue. They've got multi-byte characters because their character sets are so large they don't fit in a single byte. The most common one you'll see nowadays is UTF. There's UTF-8, which is 8 bits, which can be increased to more than 1 byte based on the character. UTF-16 and UTF-24. Basically, what you'll see most often is UTF-8. You can have occasions where you can widen a character to convert it to a wide character. Narrow goes from wide to narrow. But this is the type of thing that this is on a character by character basis, a little bit troublesome. You're probably better off, if you need to handle international character sets such as the Asian characters, is to look up and find a library to use and call a library, which will probably override the input and output file streams and the IO streams in order to handle your international character sets. So, are we confused yet, or do we go in the outdoor, or do we go out the indoor? Anyhow, that's it for today's lesson on intermediate C++, which we will see you next time at educator.com.